Hello my dears, how are you all? So today we are going to discuss about the concept of ideal diode. Ideal diode. So what is meant by an ideal diode, my dears? Ideal diode means a diode, it's in ideal form, which is nothing but under forward biased condition it offers zero resistance, and under reverse biased condition it offers infinite resistance. Then it is the property that an ideal diode exhibit. But in practical case it never exists, right? Because ideal one never exists in real life. So in a ideal diode, an ideal diode VA characteristics can be represented like, my dear, listen. This is the voltage V and this is the current I. Then this will be the ideal diode's VA characteristics. From this simple graph now, it looks like a very simple graph, but it tells you a lot. It tells you a lot. It tells us a lot, right? See. So ideal diode means what, my dear? The forward resistance will be equal to 0 ohm and a reverse resistance will be equal to infinity, right? Infinity ohm. So when this forward resistance will be 0 means it happens only when V by I is equal to what? 0. When the V by I will be 0, that means, which implies we have some value. That means, we have 0 and I have some value. Then only the term will be equal to 0, right? This is R is nothing but this is the forward resistance. RF is nothing but V by I, which is equal to 0 implies 0 divided by some value. Am I right? 0 divided by some value. So 0 divided by some value means in graphically it can be represented like, listen my dear, it is like what? 0, the voltage is 0 here. Na? In this axis the voltage is 0. So 0 divided by some value of current will give you the forward resistance to 0. Is it correct? Okay. And what is RR is equal to infinity? What do you mean by RR is equal to infinity, my dear? RR equal to infinity is nothing but V by I is equal to infinity, which implies that some value divided by 0 will give you an infinity. Am I right? Some value divided by 0 will give you the value of infinity. That is, from this graph itself it is clear that there is a current, there is a voltage V. At that time the current is 0. That means there is some reverse voltage. Why this is not here? Because we are in reverse biased condition only, this reverse resistance is calculated, right? So in reverse biased condition, whenever there is a voltage, reverse voltage, even though there is a reverse voltage, the current is equal to 0. That means some value of reverse voltage will be there, divided by 0 will make you the resistance to infinity. So simply it shows a graph, but it tells us a lot. It tells us a lot, my dear. So that is the peculiarity of this graph. That is all about the ideal diode. Then what happened to the practical diode, my dear? Practical diode. So in practical diode, there will be a small voltage exist in the forward biased condition for any semiconductor if you are taken. That means normally the forward resistance is equal to 0 ohm now. How that 0 ohm happened? V by I. That V is nothing but 0 volt. That means in the forward biased condition there will not be any drop across the diode. In other way we can say like this. In forward biased condition there will not be any voltage drop across the potential barrier or across the diode. Is it clear? So in practical diode, my dear, a practical diode can be represented like a resistance and a drop. So this is called the forward resistance and this is called the cut-in voltage. This is nothing but our anode and this is nothing but our cathode. Okay, cut-in voltage. This cut-in voltage Vy is nothing but, my dear, it is 0.3 volt for germanium and which is equal to 0.7 volt for silicon. These things you have to note. You know this now, you know this, I know. So this equivalent circuit is very, very important. A forward resistance and a drop. This drop is nothing but, my dear, it is the voltage required to break the potential barrier, that's all. That is represented by this cut-in voltage or Vy. This voltage is, I have already explained now, cut-in voltage. This is called what, my dear? Cut-in voltage. So this cut-in voltage is nothing but the voltage across the what? Diode. Diode in the sense voltage across the potential barrier, that's all. And what happened to this is for forward biased condition. Then what is the equivalent circuit in reverse biased condition? Reverse biased condition. So reverse biased condition is simply represented by a resistor. A reverse resistor, anode and cathode. PN is also represented like anode and cathode. Anode is the positive terminal and cathode is the negative terminal or N region. This is nothing but RR. And this is the equivalent circuit of what? Reversed biased diode. So I can represent like this is forward biased, and this is nothing but, my dear, reverse biased. Reverse biased. You have to note this. So these two equivalent circuits you have to note. And also, my dear, this forward resistance and reverse resistance comparison. Normally the reverse resistance is much higher than the forward resistance. Okay, so the forward resistance will be in the range of 10 ohm to 100 ohm normally, and the reverse resistance will be in the range of some mega ohms. This pattern also, or this range also you have to remember. So that is the concept of practical diode. So this is nothing but the ideal diode. Ideal diode is nothing but this term you have to note, my dear. This term you have to note. And as a competitive examination point of view, this is very important. RF is equal to 0 and RR is equal to infinity. RF is equal to 0, in other words, there will not be any voltage drop across the potential barrier of the diode. That means if it is an ideal diode, what happens means simply it offers a forward resistance. Okay, it simply offers 0 forward resistance and it's simply a short circuit, that's all. If it is an ideal diode, mean A to K, anode to cathode is simply a short circuit. There will not be any Vy, there will not be any RF, because RF is equal to 0 for ideal case. In the case of practical diode, my dear, what? In the case of a practical diode, anode to cathode will be a short circuit or open circuit. Tell me, a short circuit or open circuit? It will be like an open circuit, because in open circuit condition only infinity resistance exists, right? So anode to cathode there will be what? An open circuit in the case of a ideal diode. Then only that RR will become infinity. Is it clear? So you have to compare this all things, okay? Then only things will be smoother. Okay. Next you have to see the VA characteristics of a diode. You know this very well. You know this, but we will discuss what is it. And I have bought 2 LED tube lights for that, so that for improving the quality, right? Improving the quality. And I myself felt that my videos are but slightly darker, right? Slightly, it is not light visibility, or the light is not there, adequate light is not there. So I bought 2 LED lamps. So that's why you might feel there is a change in our lecture compared to the previous. Okay. I want to give you maximum quality and minimum budget because our channel didn't start, or our channel didn't get any money. If our channel is monetized, if our channel grows bigger, then definitely we will buy some very good gadgets for teaching purpose, and we will change our teaching style to digital like that digital panel board, that big IFB board, etc. It costs very high, so we will try. If God's grace, our channel is improving. Now it is improving, it's growing now. So with all your support, if it is growing, and if our channel gets monetized, definitely I will give priority to, first of all, to improve the lecture in the sense improving the gadgets which is used for the teaching purpose. Definitely I will buy one, okay, and definitely I will give you very quality video lectures so that it will be remembered for long time. So that's my wish. Teaching is my passion actually. Okay, now listen. So next you have to see VA characteristics of diode, my dear. VA characteristics of diode. VA characteristics of diode. This I know. So this is V and this is I, my dears. This is I0. So reverse leakage current. Cut-in voltage. Okay. Reverse pattern, cut-in voltage. So listen, my dear. Reverse leakage current you may mark like. Okay. This is a reverse leakage current, the small current, okay, in the reverse. But this is called breakdown. This is called breakdown current. This is breakdown voltage and this is called the breakdown current. Okay. IBR. Breakdown current. Listen, my dears, listen. And this is, you should note one thing here, it is non-linear. It is non-linear. So this is the VA characteristics of a diode, my dear. We know that for forward, when it is in forward bias condition, even if you apply some voltages, it will not conduct. And after a particular voltage called the cut-in voltage, the diodes depletion layer gets breakdown and it will conduct. Okay, and this is nothing but the reverse. Whenever the diode is a reverse bias condition, if you are increasing the voltage in the reverse bias, a small current starts flowing in the in reverse manner. That is called the reverse leakage current. It is due to the minority carriers. And after that, even if you even you increasing the voltage in the reverse direction, suddenly what happens, my dear, the diode's depletion layer it will become wider and wider and it will burst. It will burst. And due to that, there will be a sudden inertia current which is flowing in the reverse direction, which is called the reverse breakdown current. Reverse breakdown current. And one more thing you have to note here. This I0 for germanium will be greater than I0 for silicon. That means the reverse leakage current of the germanium will be higher than the reverse leakage current of the silicon. That is one of the reasons I already told you. Silicon is nowadays we use silicon because of this reason, because its reverse leakage current is very less compared to the germanium. Okay, so that is the VA characteristics. And along with that, we have to mention two terms, my dears. First one is static resistance. And second one is dynamic resistance. So static resistance is nothing but, my dear. Static resistance corresponds to, I will write here, that is better. Static resistance or DC resistance. Okay, it is nothing but, my dear, a particular value of voltage divided by the particular value of current. Say, let be V1 and let be I1, which is called the static resistance. And of course, this is in DC image. That means whenever or the resistance offered by the conductor, or resistance offered by the diode, it is in forward condition. These two, the static as well as the dynamic resistance, comes only under the forward biased condition. Forward biased condition. Okay, or this is nothing but forward resistance. This is nothing but forward resistance. Both the static as well as the dynamic resistance comes under the forward resistance because it is measured only when the diode is in forward biased condition. So what is meant by the static resistance, my dear? Whenever we are applying DC voltage to the diode and measure the DC current corresponding to any voltage value, that is called the what? DC resistance or static resistance. Other resistance is called the dynamic resistance. Dynamic resistance or AC resistance, which is nothing but what, my dear? Similarly, delta V divided by delta I, that is nothing but AC in nature. That means whenever you took now V1 divided by I1, that is a particular value. Similarly, if you have taken for change in voltage V1 to V2 to I1 to I2. So this change in current delta I to the change in voltage, this voltage, this is nothing but delta V. So delta V to delta I. So graphically I will mark like this. Graphically we can mark like this. Is there delta V to delta I? This delta V to delta I is called the what, my dear? Dynamic resistance. For competitive examination point of view, you have to note one thing only, my dear. Here, RDC very much greater than RAC. This thing you have to note. That is very important in terms of competitive exam point of view. So DC resistance or the static resistance is always very much higher than that of the dynamic resistance or AC resistance. That is only we need from this session. Okay, is it clear, my dear? Is it clear? Next one, diode current equation. What's the time now? Let me check. Yeah. Diode current. The diode current is nothing but, my dear, ID is nothing but I0, or you can say corresponding temperature. That is very good. That is really interesting. You can take for temperature, my dear. The diode current equation is I0 at T2, temperature will be equal to I0 at T1 into 2 raised to T2 minus T1 divided by 10. This equation is very, very important, my dear. This equation is very, very important. So as far as the diode concerned, this equation is very, very important. That means the diode current is much affected by the temperature variation, because the temperature itself acts as an energy, because it will supply some amount of energy to the carrier so that the carrier will be increased whenever we are increasing the temperature. We already discussed the relationship with respect to temperature in semiconductor as well as the conductor. We already discussed it. So in the case of a semiconductor, my dear, whenever we are increasing the temperature, what happened? It is to be said that every 10 degree Celsius rise in temperature leads to doubling of diode current. Doubling of diode current. Okay, doubling of diode current. And this is nothing but, my dear, this I0 means nothing but reverse current, reverse current. Reverse current. So diode current in reverse current, or no, reverse current you can write. Reverse biased condition or reverse biased current. There are forward current also, no? We don't want to confuse with that. So diode current in reverse biased condition, that is correct. So I0 is nothing but reverse leakage current or reverse leakage current. So reverse leakage current is much affected by the temperature variation because it is due to the minority carriers. So whenever again we are increasing the temperature, what happens, the more and more minority carrier get liberated from its atomic structure, so that it will also take part in the conduction in the reverse biased condition. So the every 10 degrees, how can it be checked that? Suppose it is 10 degrees, suppose T1 is equal to 10 degrees, you imagine. T2 become 20 degrees, you imagine. So 20 minus 10 is nothing but, my dear, 10. So 10 divided by, so every 10 degrees Celsius rise now, every 10 degrees Celsius rise means I can say like every, see, suppose it is 10 and suppose T2 is 20. So 10 to 20 means 10 degree, 10 by 10 means 1, 2 raised to 1 means 2. So I0 of T2 is equal to I0 of T1 into 2. That means at T2, 2 times of T1 happened, right? That's all. That is, it is written here. Every 10 degree rise in the temperature leads to doubling of diode current. Doubling of diode current. I will mention here in reverse biased condition. Reverse biased condition. Okay, that is the dependence of temperature with respect to the reverse current in a diode. Okay, what is the general diode current equation? General diode current equation. General diode current equation. That means it is applicable to both forward as well as the reverse biased condition of the diode. Okay, general diode current equation, which is nothing but, my dear, ID is equal to I0 into e raised to Vd divided by eta Vt minus 1. This equation you have to remember. This equation is very, very important. Where ID is nothing but diode current, and I0 is nothing but minus initial current. Initial current, and Vd is nothing but diode voltage or applied voltage, and Vt is nothing but thermal voltage, and eta is called a recombination constant. It is called a recombination constant or recombination voltage. And its value will be equal to 1 for germanium and 2, eta equal to 2 for silicon. This thing you have to note down. This thing you have to note down. Okay, so that is the general diode equation. General diode current equation. So in the forward biased condition, in forward biased condition, I can say that e raised to Vd divided by eta Vt much greater than 1. So I can write the diode equation, diode current equation as ID is equal to I0 and e raised to Vd divided by eta Vt only. Minus 1 you can neglect. This means nothing but it's an exponentially increasing curve. Exponentially increasing curve. That's why the forward characteristics now look like this, exponentially increasing curve. Okay. In the case of a reverse biased condition, in reverse biased condition, e raised to Vd divided by eta Vt much less than 1. So Id will be equal to minus I0, because Vd minus 1 much less than 1 means this term can be neglected in the diode general equation, so that this term will be 0. So this term minus 1 will be the result. I will explain here. This is Id is equal to I0 into e raised to Vd divided by eta Vt minus 1 general equation. If this is not exists, simply Id is equal to minus I0. Correct? That's why it is equal to minus I0. That means the curve will look like this one, minus I0. This value is nothing but minus I0. That is the diode is in reverse biased condition. This term is entirely different. It is in a breakdown region. That is not our cup of tea. A cup of tea in the sense, it is not our area of interest. Our area of interest is nothing but whole forward region plus the reverse leakage region. But this straight line region, it is the breakdown region. That is uncontrolled region. Both the forward, complete forward region that we can control, and the reverse leakage current I0 up to I0 max we can control. But that flow this flow that we can't control. At VBR, reverse breakdown happened. The diode will be destroyed there. The diode will be destroyed there. So this is we cannot control. So this I0 is minus I0. That's all. This I0 is minus I0. So these two equations you have to note. So this is, I can say that this is nothing but minus, my dear, Id equal to minus I0 means simply negative constant. Not called as negative current. Negative current. Is it clear? So these two equations you have to note down. This is for forward biased condition, exponentially increasing current, and this is for the reverse biased condition, which is nothing but a reverse current, which is nothing but, my dear, a reverse current, which is nothing but a reverse current. Is it clear? Is it clear? Okay, next one, diode capacitance. Diode capacitance. So I would already mention, my dear, see, suppose if you are taking a PN junction diode like this. This is the PN junction. This is nothing but P and this is nothing but N. So there in between there will be a capacitance because of the diffusion of charge carriers, already explained yesterday. So this is nothing but the diode, the diode potential or the depletion potential, correct, depletion potential, and this is nothing but the depletion layer. This is nothing but the depletion layer. So whenever we connect it to an external terminal, my dear, whenever we connect it to an external terminal, it will lead to a forward as well as a reverse condition. It will lead to either forward or reverse condition. So there are two types of capacitance exist in a PN junction diode. First one is diffusion capacitance. First one is diffusion capacitance and next one is the transition capacitance. Transition capacitance. So this diffusion capacitance occur when it is in forward biased condition. And this happens when it is in reverse biased condition. Now there are two types of capacitance exist there. It is nothing but the forward biased condition, it is called the diffusion capacitance, and another one is nothing but the transition capacitance. See, when it is in forward biased condition, what happened to the width of the depletion layer? Whether it be increased or decreased, the width of the depletion layer will be decreased in forward biased condition. So that the general equation for capacitance is nothing but capacitance C is equal to epsilon A by D, where D is nothing but the distance between the plates. Right, distance between the plates. So what happened, my dear, if you are increasing the forward biased voltage, the width of the depletion layer become decreases. That means this will become very lesser, so that high capacitance will be higher. So that is why in forward biased condition, the barrier will not be exist. Actually, in literally there will not be any depletion layer, but in actual practice, now narrow line you can see. That means the capacitance will be very high at that place. That is why this depletion capacitance will be very high. And in transition capacitance, nothing but is in reverse biased condition. That means the depth will be very high, D will be very high, so that C will be lesser as compared to the diffusion capacitance. So generally we can say that diffusion capacitance will be at least greater than 500 times of CT. CD greater than at least 500 times of CT, or not greater than, it is nearly equal to. CD very greater than CT, or CD nearly 500 times as that of the CT. That is, the diffusion capacitance is much higher than that of the diffusion capacitance. Okay, that also you have to note there. That is the diode capacitance condition. So there are two types of capacitors only you have to define. Examination point of view, this word is very important. Diffusion is in forward biased condition, transition is in reverse biased condition. That only you have to note from here. That only you have to note from here, my dear. Okay, is it clear? So that's all about the diode. That's all about the